Good evening, all. Welcome to the live session for the course Matlab Programming for Numerical Computation. So let's wait for 2-3 minutes more to see if there are more students to join the session, and then we'll start. So whoever is there in the meet, in the Zoom links, please stay here, okay? And we'll start soon. Please mute yourself if you don't have any questions. So let's begin today's session. So this week will be, as we used to do in our previous classes. First, we'll have a quick recap of whatever we discussed this week, and then we'll try to solve a few problems. Those are similar to the assignment questions that you will be getting. So in case you have any doubts, please do unmute yourself and ask me then and there, or else you can just put it in the chat box and I'll answer it. So here we'll be trying to, this week we are discussing about solving ordinary differential equation. So I hope that you guys know what is ordinary differential equation. So that is, you will have some equation in the form of d by dt. And this right now in this week we'll be solving ODE with a single variable. Okay, we'll come to that. So first of all, let us understand what is the aim. What are we looking at? What do we need to find out here? So what are we doing when we are numerically solving the ordinary differential equation? So for example, imagine you have like a function or imagine like a function that is y and that is varying with respect to time. So you know that the initial and when the time t is equal to 0, you know what the y value is. So when you're something, for example, maybe you were starting an experiment. So at the initial time, you know that when t is equal to 0, you know the y value. And in the next case, what you know is how how y changes. For example, you know what is dy by dt. That is what is dy by dt. Dy by dt is nothing but change of y with respect to time, right? So you know just two parameters here. So just give me a second. Let me just annotate. So here we have like two parameters. One is, at t equal to 0, you know what is the y value, and you know what is dy by dt. That is basically change of y with respect to time. So these are the two infos that we know. Now the aim is we need to find out how y changes with respect to time. For example, if we have a particular time given as t1, you need to find the corresponding y value. Okay, so that's how we need to understand. We need to have a table like this. That is, when t equal to 0, you know the y value. Now, when the t keeps changing, how does the y value keeps changing? Okay, so that's what we are trying to study while numerically solving the ordinary differential equation. Do you have any doubts in this part? Yeah, Megastri. If you don't have any questions, please do unmute yourself. Don't disturb the class. Only, excuse me.
Ma'am, I'm speaking to you, ma'am.
Yeah, do you have a doubt?
No, ma'am. As now, no.
Also, please
No.
mute yourself.
Okay, ma'am. Okay.
Yeah. Okay. So this is what we are trying to do here. So we compute the nearby y of t using what we already know and then repeat. That is, you know what at t equal to 0, you know the y value. Okay. Now we utilize this information and calculate when t equal to 1. Okay, you get a particular y value. And using this equation, you calculate at t equal to 2, what is a y value. So you start with what you already know and then you progress forward. So that's what we are trying to do this week. So the first thing is ordinary differential equation IVP. So IVP means it is initial value problem. That is initial value problem. You would have already also learned about BVP, which is boundary value problem. We'll come to that later in the class. So this week we'll not be discussing this. So this week what we are trying to do is ODE, initial value problem. So what is meant by ordinary differential equation? You will have a function dy by dt. Okay, you know how the y is changing. So y is changing in some form, which is a function of both t and y. Time, it could be t, it could be x, it could be the independent variable, could be anything. It could be position, time, whatever it is. And then you know initial value problem means you know how the initial state of the system is. That is, when t equal to 0, your y value is y0. Now what we need to find is for any random what we need to find is for any random value of ti, you need to find the corresponding yi. So this is what we need to find out. So now what we do is, you know this equation, that is the, you know how to find the derivative of a particular variable, derivative of a particular function from the Taylor series expansion. So let us look at that. So imagine that you have a y, you know the y value at I. Okay, you know at I, the y value, you know it. Okay, this is known to you. Okay. And if you know the I value at I plus 1 also, if you know the value, what is it? You can take the difference of this, divide by the step size between these two, that is h. But provided that h is a very, very small value, when you do this, what do you get? You get the derivative of the function. That is dy by dt. That's what you get, right? So from this, if you do a small rearrangement, what will happen? Let's imagine that, okay, we are assuming h to be a very small value. You take h to this side, and then what do you do? This vi also you take the other side, then you get this particular equation. That is vi plus 1 is equal to vi plus h fi. What is fi? Fi is this particular value. I'm calling it as fi. Oh, sorry, this is not okay. You can't call this as fi. So fi means, remember, fi is the function, this value at t equal to I. Okay, so at f t comma y, this function, if you're putting t equal to ti, you get fi. So basically, this is the derivative value when t equal to ti. So what happens? You know the starting value of y. H is a very, very small value that you take. It could be 0 0.01, 0 0.1 or something like that. And this is a slope at that particular So this is a slope, right? This is a slope at the particular t equal to ti. And then when you do this, you will get the what is the y value at the next point. That is at the I plus 1th point, you will be finding the value. Then this formula, this update formula is called as the Euler's explicit. Sorry, this formula is called as the Euler's explicit method. So I'll repeat it once again. So when you're starting with your calculation, you know the y. So let us imagine that I is equal to, in just a second. So let us imagine I is equal to 0. So what do you know? You know what is y0 and you know what is f0. F0 is nothing but this equation. Okay, this equation that you have here. Now what do you do? How do you calculate y1? Y1 is equal to y0 plus h times f0. Now we get y1. Now what do? You can also calculate. So now what is y2? Y2 can be calculated as y1 plus h times f1. How do you get f1? Because f1 is already given as a function, right? So you have to just substitute t1 comma y1. When you substitute this, you'll be getting f1. Again, you can go here. So you'll be getting y3 is equal to y2 plus hf2. And how do you get f2? You have to just put here t2 comma y2. Y2 you've already got from this equation. So this is how you progress. Any doubts so far?
No, ma'am.
If you don't have any doubts, let us proceed further. So here we have an example question where y dash, that is nothing but dy by dt. Okay. So this is dy by dt is given as minus 2ty. You know the initial value, that is a t equal to 0, y is equal to 1. This is the initial value that we have. And the analytical solution. In analytical way, how do you find out? You know the dy by dt that is given to you. Okay, minus 2ty. What you have to do is you have to just integrate it. When you integrate, you will be getting y is equal to, so in this case, this is the value. Okay, exponential minus t square. Okay, this is the value that we'll be getting when you integrate it. Okay, so let us try to solve this using the Euler's explicit method. So before that, let me just show the Matlab code. Just give me a second. Hmm. I hope you can see Matlab. Okay. So first is Euler's explicit equation. This is a code which has been already shared to you in the recorded lectures. We'll just go through it one by one. Okay. So the function which we are trying to is there a problem here? Are you guys able to see my share screen?
Yes, ma'am.
Yes.
Okay, just a second. Okay. Okay. So what we do is just give me a second. So what we try to do is, let's begin from this term. That is the function we are trying to solve is y is equal to minus 2ty. And the information that we have is y0 is equal to yeah. And the information that we have is okay. Sorry, there is like a small connection issue for me. Okay. And the information that we have is at t equal to 0, at t equal to 0, y is equal to 1. So this is what we declare, that the t0 be equal to 0 and the corresponding y value is 1. And then what happens? For every time when you're doing integration, analytically also you need a limit, right? When you're integrating, you need a upper limit and a lower limit. And you know the lower limit is 0 because that has been given to you. And the upper limit, let me fix it to be 5 or like some value. Okay, depending on what you want. So here what I am fixing is, here my 5 is my upper value. Now what I do is, you know that I need to take a value which is very small. So right now I've taken a value of 0.001. H is equal to 0.001. Now what you do is, you know, it's an iterative method, right? So this method is like one particular formula has to be repeated some n number of times. So for that you use a for loop, and you have to tell for loop how many times it has to run. So what happens is, you have to run it for n times. And how do you calculate the n? So calculating the n is very pretty straightforward. That is, you subtract the limits. So this is 5 minus 0 divided by 0.01. So whatever value that you get, that is the number of times you have to run the loop. Okay, so this is the n value, Tn minus T0 divided by h. Now what you do is, as an answer to this question, what you should be getting is, you should be getting a vector T, and you should be getting a vector y. So this has to be a vector, this has to be a vector. So initially let me declare all the t values. Initially I know what the t value looks like. The t value has to be, it starts from 0, then the step size is 0.001, then 0.002, like that it should go till t equal to 5. So this is what my t vector looks like. So let me declare that t vector is t0 with the step size of h till tn. This is a row vector. When I put this thing, you get a column vector. Okay, you get a column vector. Now next is, I have to declare the y values. So the y value, you only know what is happening initially. I know when t equal to 0, y value is equal to 1. Rest of the values I don't know. So what do? I declare everything to be 0 initially. So all the entries are 0 to begin with. And then I say that let the first value of y be y0. So then what happens? It becomes 1, 0, 0, 0, 0. Okay, so that's what happens. Okay, is this clear? So far, is this clear till this part? Okay. If that is clear, then what we have to do is, we have to apply the Euler's explicit formula. So we run a for loop. Uh, so so we run a for loop, and the for loop has to be run n times, 1 to n times. And then what do? We have to calculate the Euler's explicit formula. So that is this. That is Vi plus 1 is equal to Vi plus H times Fi. And what is Fi? So that before that you have to calculate Fi value. Fi value is nothing but it is given to you, that is 2Ti, where for calculating, when you have to calculate Fi, it has to be minus 2 Ti Yi, right? So that's what you do here, minus 2 Ti capital Yi. These are my vectors. So what happens? I calculate Fi first. I substitute the Fi value here. Then I calculate the next Y value. Okay, so this is what I do. Okay. So this is what we do. Now what do you do in the next is, in the code, you've got all the Y values, and here you've got all the Y values corresponding to the T values. Now we have to plot it. For plotting, you plot the T versus Y with a line width of 1.5, and the color is red, and the line style has to be like dashed lines. I'm adding an X label T, Y label Y, and this is a true function. I'm just trying to compare how my results are compared to the true behavior of a function. So the true function is exponential minus T square. So what I do is, for the same T, I try to calculate the Y true value. So here the T is a vector. When I put in this equation, I get Y true B also to be a vector. So I plot that too, and the color is black. And I also try to calculate the error. So error, how do you calculate? This is the true value, which is a vector, and Y is also a vector. You subtract. So what do you get? You get an error, which is again a vector. So out of that, let me just see how the maximum error is. So that is max of error. You'll be getting the maximum error here. So after running this, so let's just a second. So this is how the graph looks like. Okay. So I'm not sure if you can carefully see it. Actually, there are two graphs here. Okay. Yeah, see. There are two graphs here. One corresponds to the true value and the other corresponds to what you got using the Euler's explicit formula. And you can see actually it's a very good match. Whatever you get, there is a difference, but it's a very good match. The overall behavior is a very good match. You can see it runs from t equal to 0. You can see that it runs from t equal to 0 to t equal to 5. And also you can see that at t equal to 0, what is the y value? Y value is 1. So these things are given to you in the question and this has to match. Okay. When t equal to 0, y value is 1 and it is decreasing and you have calculated the value from t equal to 0 to t equal to 5. And let us calculate the maximum error and the maximum error is 3.255 e raised to minus 0.04. Now what happens is let me just increase the h value. So h was initially 0.01. Now when I calculate again this, I am getting the same kind of a behavior. But sorry, I didn't run it properly. Okay, I'm getting a similar behavior, but you can see how the error is. This was of the order of e raised to minus 0.4 and this is the order of e raised to minus 0.3. So initially it was e raised to minus 0.4, then it became e raised to minus 0.3. Okay, that is like a factor of 10. And also the h value also I decreased by a factor of 10. So what does this mean? When I'm increasing my h by a value of 10, by a factor of 10, my error is also increasing by a factor of 10. So which means that this method is nothing but a for the order of this method is 1. Okay, order of this method is 1. Any doubt so far?
Ma'am, that order part alone, can you explain once again?
So the
Order.
order what we have done is in all the previous classes we have done something. That is, how do you understand the order of a method? So order of a method is you see that how this h value, that's the step size value that it is taking for any particular calculation, is related to the error. Okay, so then what you do is for this particular h value, just give me a second. Yeah. For a particular h value, you calculate the error, and the other h value, you calculate the error. Now you see how much you have decreased this factor. So it has decreased by a factor of 10. So earlier h value was 0.01, 0.001, right? Let me just check what was the previous h value. Let me just see here. Yeah. So the initial h value was 2 zeros were there. Okay. So when h value is equal to 0.001, my error value was of the order of e raised to minus 0.4. When I increased my h value by a factor of 10, so that is I increasing the value by a factor of 10 means it becomes 0.01 and the error is also decreased by a error is also increased by a factor of 10. See, this is of the order of 3.3 e raised to minus 0.3. This is 3.25 e raised to minus 0.4. Okay, so this is a factor of 10. And how do you say the order? You say the order has how much is this, you say this n to be the order. Okay, here the factor is just 10 raised to 1. So n is equal to 1. So this you say first order method. So what happens is if you had decreased h by a factor of 10 and the error goes by a factor of 100, this is what is 100? 100 is 10 raised to 2. Okay, then you say that n is equal to 2 and that is the order of accuracy. Okay, now there might be other method where you decrease h by a factor of 10, the error goes by a factor of 1000. So what is that? 10 raised to 3 and the order is nothing but order will be 3. Okay, and there is one more way you find out. You can calculate the log plot and you can calculate the slope of it. We'll do that in an experiment and we'll try to see that. Okay, how does that change? Is this clear? How do you say the order of accuracy of a particular method?
Oh, yes.
Yeah. Now moving on to the next method, which is the Euler's implicit method. So far we had an explicit method, right? Okay, so far we had an explicit method. Next is Euler's implicit method. So that method is you have the same formula sorry, you have a same kind of a formula, that is yi plus 1 is equal to, okay, so that is yi plus 1 is equal to yi plus h times f. But remember this f earlier, it was f calculated at ti comma yi. Okay, this is Euler's explicit. But in implicit formula, what happens is, okay, it will be at ti plus 1 and yi plus 1. But here there is a problem. You can see that both yi plus 1 is there in the left hand side and the right hand side. Okay, so you can directly calculate it, because for calculating this yi plus 1, you need to calculate this side of the equation, which again has yi plus 1. So that is why when you have such a kind of a problem where the same variable is there in both the LHS side and the RHS side, you try to solve it using fsolve. Okay, you have seen this in the previous classes, how to use fsolve. So how do you do it? When you have to do fsolve, what you do is you have to write this function in the form of f of x is equal to 0. So what do? You bring everything towards one side. You're bringing everything towards the one side, so it forms an equation like this. So this is your equation, and you equate it to 0. And you can, there is a fsolve, there is a standard syntax. Okay, so this is the syntax of fsolve. Just a second. Okay, this is the syntax of fsolve. So in fsolve, what you have to do is, if you have a function in the form of f of x is equal to 0, you put that function in a Matlab function name as f1 name. Okay, so the fun name, if for example, if your function was y minus x is equal to 0, you create a Matlab function, okay, and it gives an output, then you have the fun name and the input and here what you have as an output should be nothing but your y minus x. Basically your function should be the output. Okay, this is how you write the Matlab function. So this fun name is the function that you're trying to solve, and for solving the function you have to give an initial guess, that is called as x0, and whatever the answer that you get will be the solution that is satisfying this particular equation, and that is saved in xsolve. So again, I'll read it here. Xsolve is a resulting solution. Funname is a function that provides how to calculate f of x, and x0 is the initial guess. It has to be the same dimension of the variable. So here we are only talking about single variables. It will be a single scalar value. Any doubts? So, okay. So let's try to solve this method. Using this method, let us try to solve the same question. That is, y dash is equal to minus 2ty. At t equal to 0, your y value is equal to 1. And the actual solution is y of t is equal to exponential of minus t square. So let me share Matlab. Hmm. So everything remains the same. You're calculating at t equal to 0, your y0 is equal to 1. And at t end is equal to 5. Okay, you're calculating from 0 to 5. That is your integration limit. Now I'm calculating for an h value equal to 0.1. Okay, I can take a smaller h value also. That is completely fine. Now I have to calculate how many times my loop has to run. So that calculation comes from tn minus t0 divided by h. I get the number of times. Then what I do, I have to declare the t and the y vector. T I already know it has to go from 0 to 5 with the step size of h, which is 0.1 here. And y, initially I don't know what is the value, so I declare everything to be zeros. And after that, I know what's the starting value. So I declare the first starting value to be y0 that is given in the question. Okay, that is this one. So now my t and y vectors has been initialized properly. Now what I do is I calculate using the Euler's implicit method. I run the loop from 1 to n times. Okay, I have to calculate, I have to solve this problem. Okay, this is my problem here. So my function is of the form. Okay, so let's try to write that. So yi plus 1 minus yi minus h times f of yi plus 1 comma ti plus 1. Okay, this function is equal to 0. This is a function that I have. So let me do one thing. I'm just calling t to be ti plus 1. Okay, this thing I'm just calling it to be this thing I calculate. Now what I do? So now it will become Hmm. Just a second. Yeah. Now what I'll do is I know what is the y value. This ti plus 1 and this is the variable I have to solve for. Okay, this is the variable I have to solve for because it is there on both the sides. So let me just call it y. And the yi value I get it from the my vector. Okay. Now what I do is minus h times that is also there in the vector. And what is my function value? My function value is minus 2ty, right? So that is minus 2, that is ti plus 1, yi plus 1. So ti plus 1, comma, yi plus 1 is equal to 0. And ti plus 1 and yi plus 1, I call nothing it by yi minus, sorry, it has to be plus 2h t y is equal to 0. Okay, is this clear? And here t is not a variable. It's a scalar value. That y is all you know what is ti plus h also you know what is this value. So here the only unknown is y. Okay, y is the only unknown we have. So this is a function here, the same function that I calculated. Now what I do, I need to solve using fsolve. You have to tell which variable I have to solve for. So I'm trying to solve it for y, and my initial value is nothing but yi. That is my initial guess that I'm giving. And options is this is like an additional thing. So in options, I'm telling that solve this equation using fsolve. And then my maximum iteration, this calculation should go on is 1000 iterations. Okay. So once I get it, I get a y solution. In the y solution, it will be nothing but it will be a yi plus 1. Ti plus 1, you already know. You know the yi plus 1 will be the small y that you get outside of this fsolve function. Is this clear? Any doubts? Yes.
Plus 1 minus y, the calculation part you have mentioned, right?
Can you repeat it again? Which calculation part?
The calculation is y plus 1 minus yi.
Calculation. If I understand it correctly, you're talking about calculation of yi plus 1. Is it right?
Yes, yes.
Okay. So what I do is, you know this equation, okay? You know this equation. We had already seen it in the PPT. So let's go back to the PPT once, just to refresh. Okay. So this was the equation that we had. Okay. So the same equation. Just a second. Okay, you know this equation that is already been given here. So let's keep a note of that. Vi plus 1 minus h of f ti plus 1 yi plus 1 minus f minus yi. Okay, so that equation let us write here. Okay, so when you write it here, it will be just a second. Yeah, it will be yi plus 1 minus h times f of yi plus 1 comma ti plus 1, and it will be minus yi is equal to 0. Is this formula right? Okay. So let me just tell what is ti plus 1 and yi plus 1. So if I know what is ti plus 1? Ti plus 1 is nothing but ti plus h. Okay. So what I do? I write yi plus 1 is equal minus h times f of yi plus 1, and this thing you can directly, so here if you see this part is called as here, it's here. Okay, so ti plus h, I'm calling it small letter t. So let me just write it here, t minus yi is equal to 0. This is the equation, right? Now what I do is I want the whole aim of this equation is I need to find the value of yi plus 1. Okay, so this yi plus 1 let me call small letter y. Okay, this yi plus 1 I'm calling small letter y. So y minus h f times y comma t minus yi is equal to 0. What is yi? You already know what is the value of yi. So initially when you start, yi is nothing but 1. Okay, that is nothing but your y, capital Y vectors first index, okay, is equal to 0 minus h f y comma t y minus. Okay, now here in this case, what is your fyt? This is minus 2ty, right? So it will become y minus h minus 2ty minus capital Y I equal to 0. That is y plus 2h t y minus yi equal to 0. Okay. So now what happens is when I start my equation, I know what is yi. That is nothing but 1. I know what is t because already I have calculated the vector t here. Okay, that the entire t vector is known to me. Okay, I know what is t. Now the only unknown is h is also known because h I take the initial value. So h is here 0.1. So now the only unknown is y here. Okay, so that's how you calculate. The only unknown is y here. So that is what you see in the equation. y plus h 2ty. So basically this one minus capital yi. This is the equation that you're trying to solve. This is equating it to 0. So when you solve it in fsolve, this is how you write the function. Have I solved your doubt or do you still have doubt? Okay. I didn't understand what you said, but I hope it is clear. Okay. So this is how you use fsolve. The solution of fsolve, you will be getting the solution here. Whatever y it was supposed to come, that solution you will be getting it here. What is that y? That y is nothing but yi plus 1. That is the initial substitution that we gave, right? So yi plus 1 is nothing but y. So now you just have, after running it for n times, what will happen is for every different values of t, you will get the y value. Let me just plot it just like we did earlier. Okay, so now what happens is if you go back to the initial portion, you can see this is how fsolve solves. Okay, fsolve, these are the options, and the equation was solved for the first interval, that is the first for loop. Again, the equation was running, again equation was solved, so it runs for n times. Okay, as per the loop. Now what happens is you get the, I'll just plot the graph here. Okay, so this is how the graph behaves. You can see how close the actual solution is to the true solution. And the maximum error is 0.0302. So let me just check what is the error for 0.01. See, it's running so many times. This will take a bit of time because it has to solve the equation. Okay, so this also the maximum error is less only, but the error is more compared to the Euler's explicit method. For the same h value, the error is more for the Euler's implicit method compared to the Euler's explicit method. Okay, so in general, what we say is Euler's explicit method is a more general method where you don't have to use fsolve. So that method is a more general method, and that is what we prefer also. So general assumption is unlike explicit method, Euler's implicit method. Just a second. I think I have to just show you with a larger y value, larger h value. Just a second. So now we have seen with the small h value, right? So let me just take a larger h value. Let us see how the solution looks like. So close all. Okay. This is how the graphs looks like. You can see there is like a small jumps here. This is not a very smooth line. Okay. Now let me further increase the h value to 0.5. Now if you look at the graph, you can see, sorry, I have to close the previous figure. You see, again, it is not very smooth. This was the original curve and the actual curve is not very smooth. Now I am taking a very large value of 2.5. Let me take 0.5 initially. Okay. Again, close all. Okay. I am getting still the behavior is okay. Again, increasing the value of 2 to 2.5. See, now I get a sharp dip. Okay, I lost that initial that curve-like behavior. I don't have it anymore. Okay, I'm not sharing it, I think. So this is a graph I get. I don't get that curve-like behavior anymore, but initially instead of that, I get a sharp dip. Okay, so the behavior keeps on changing. Now let me take the value h is equal to 5. See, in that I get a curve like this. So the actual behavior keeps changing according to my h value. So this is what you need to understand. Euler's implicit and Euler's explicit is very, very sensitive to the h value that you take. And Euler's explicit is a faster method because it is pretty straightforward formula. But in Euler's implicit method, it's not straightforward. You have to solve a particular equation using f solve. Okay, this will take a more number of time, like a bit more time compared to your Euler's explicit method. And it's both for both it to be very accurate, your h value has to be very, very small. Okay, any doubts?
So is the options part necessary, no? Options equal to.
No, it's not very necessary. You can remove this completely. Okay, there are some default iterations given to it. Okay, so it will run accordingly. Apart from that, you don't need options actually. It's just to ensure that your f solve is converging properly. But you can survive without options also.
Okay, ma'am.
Yeah. Now let's go on to the slides again. Now we go to a different class of method, which is called as the Rankakuta methods. Okay. So the earlier methods that we saw, that is the Euler's explicit and Euler's implicit, were first order methods. First order methods means if you're increasing, if you're making h decrease by a factor of 10 percentage, by a factor of not percentage, by a factor of 10, then the error also decreases by a factor of 10. Okay. So 10 raised to 1, which means the power is 1. So it is a first order method. Now we have a Rangakuta methods, and Rangakuta there are like different class of method. This is called as Rangakuta second order method. So it's Rangakuta RK2 methods it's called. So sorry, it's not actually, you can't directly tell that 2 corresponds to the order of the method. The actual 2 comes from, if you have a function like this, this is the update formula that we have, yi plus 1 plus yi h si. Okay, if you remember in the Euler's explicit method, what happened? In the Euler's explicit method here, uh, yeah. So in the Euler's explicit method here you had fi. Okay. Now in Rangakuta method, what happens? Since instead of fi you have si, where si is nothing but it's a combination of functions. Here what happens is k1 is a function, k2 is a function, kn is a function, and these functions are added by weighing it by a particular weight parameter. Okay, so w1, w2, etc. are scalars. Okay, and k1, k2 up to kn, they are functions of, for example, it will be in our previous case, it was a function of t and y. Okay, these are functions. And depending on how many functions you have, that is where this number comes from. So if you are using RK2 method, means you will have f1 and f2. If you have RK4, you have f1, f2, f3, and f4. Is this clear? So that's how this RK2, RK3, RK4 method is the terminology comes from. Now let us look at the first class, which is the RK2 methods. So in RK2 methods, as I said, you will have a function like this, yi plus h times k1 plus k2 by 2. So instead of having a a single fi, you have like a combination of two functions, k1 and k2. Here what is k1? K1 is nothing but f calculated ti phi a, basically fi itself. And this is a different, k2 is a function of, if when time is ti plus 1, and y is y plus hk1. Okay, so you have to calculate. So given, what happens is the same loop that you used for Euler's explicit method. What you have to do is, for calculating this, first you have to calculate k1. So what you do, so what you do is, in the for loop, first you will calculate K1 and then you will calculate K2 and then you substitute it to calculate yi plus 1. Okay, so this is the way in which you will be writing the loop. So this method is called the Huon's method and it is a RK2 method. There is another method which is called the midpoint method. In the midpoint method, it will be basically just K2 is there. Here K1 is also there, but the weight of K1 is 0. So it is 0 K1 plus some weight into K2. Okay, still it has the K1 here. Okay, so it is not a RK1 method, it's still an RK2 method. So here K1 is nothing but f of Ti yi, basically Fi. And for calculating K2, you need K1 again. So it is Ti plus h by 2 time and yi plus h k1 by 2. At this, we have to compute this first. You have to compute this first. Substitute it in your f, you will be getting the k2. Okay, I know this might be a bit confusing. When we are trying to solve the problem, it might be much more easier. So just a second. So we are trying to solve the same problem, that is minus 2ty, where y0 is equal to 1. We are trying to solve using the RK2 method. Okay. Just give me a second. So first, let's look at the Huon's method. So everything remains the same. T0 is equal to 0, y0 is equal to 1. We are calculating till Tn equal to 5. And my h, I am keeping it a very low value to be 0.1. And the n times I have to run the loop is nothing but Tn minus T0 divided by h. Now I'm initializing all the t variable from T0 to Tn with the step size of h. My y values are 0. And I'm telling the first y value is nothing but y0, the initial value that is given to me. Now I have to write the loop. And in the loop, I have to calculate K1. K1 is nothing but minus 2 Ti yi. So in our case, this is what f of Ti comma yi, and our f is nothing but minus 2 Ty. So your fi is minus 2 Ti comma yi. Okay, so this is your fi. So minus 2 Ti multiplied by yi, you get the K1 parameter. And my K2 value is calculated at Ti plus 1 and yi plus hk1. Okay, first I compute the new t, new y, and this will be my K2 parameter. You have to remember the formulas of the Huon's formula. Okay, so now I have got K1, K2. I put it together in the formula h by 2 K1 plus K2. I get the new y value. So I run it like n times. Finally, I get a similar solution. For a different values of t, I get the different values of y. So I can plot this one also. Clear? CLC. Let me run this. I'm getting the maximum error to be 0.021. Sorry. So this is the curve I get, similar to what we got earlier. At t equal to 0, y value is equal to 1. You have an exponential dip. Okay. And the error is for 0.1, the error is 0.0021. Now I'm again decreasing it by a factor of 10. Let us see what will happen to the error. Okay. The plot remains almost the same. And you can see the error is it given from 0.0021 to 1.825. So that is this, you can say it as, so this is nothing but 2.1 e raised to minus 0.3. And this became 1.82 into, sorry, e raised to minus 0.5. So it went by a factor of 100, right? 10 raised to 2. I dropped h by a factor of 10. My error dropped by a factor of 100. That is 10 raised to 2. Okay. 10 raised to 2 means this is my n value. Okay. Now the order is nothing but it is 2 for this method. This is more accurate. This is called the order of accuracy. Higher the order of accuracy, more accurate our method is. So this is the higher order method. Huon's method has an order of accuracy too. Okay. You can keep changing the h value, and if I change it by one more zero, if I add one more zero, let us see what will happen. See, this went from e raised to minus 0.5 to 0.7, again by a factor of 100. So did you understand this Huon's method? Any part, should I explain it again? Now the same thing you can do for the midpoint formula. Everything remains the same. Initializing, the vectors remains the same. Just that k1 has to be calculated as minus 2i ky and my new t value is ti plus h by 2, and yi value is yi plus hk1 by 2, and this is my k2 formula. Okay, and I substitute it in the equation, that is hk2, I get the yi plus 1. Plotting remains the same, and this also, let us look at the how the error is changing. Okay, so first I do for 0.1. My plot remains almost the same, so the error is 0.001, 0011. Again, adding one more zero here. See, so earlier this was 1.1 e raised to minus 0.3. That became 1.02 e raised to minus 0.5. So h decreased by a factor of 10. My error is decreasing by a factor of 100. That is 10 raised to 2. The 2 is my order. So both Hew's method and midpoint method are a second order method. It is more accurate than the Euler's explicit method. Okay, because in Euler's explicit method, you saw that it has only order of accuracy of 1. Okay, this is more accurate method. Rangakuta second order methods. Rangakuta RK2 methods. Okay. Is this clear? Any doubts? So now we'll look at so far we saw the mathematical methods to solve an ODE. Okay, in MATLAB, what you have to do is you already have an inbuilt MATLAB ordinary like ODE solver. You don't have to do like this is much more easier to solve using an ODE solver. So there are several ODE solvers. The name comes like ODE 45, ODE 23s, ODE 15s. There are different ODE solvers that is available, among which ODE 45 is a very commonly used ODE. Okay, and this is the ODE solver. This is the standard syntax. What you have to do is you have to use the keyword ODE45. Just a second. You have to use the keyword ODE45 and you have to tell the function. Okay, the function should have this one, dy by dt, whatever function you have. So in the previous case, the function will be minus 2ty. Okay, so that function has to be returned here for a given value of t and y. And this is my integration limits t0 to tn. So earlier it was 0 to 5. And y0 means at t equal to z0, what is my y value? In our case, it was 1. Okay, this is minus 2ty 0, 5, 1. This is how my ordinary differential equation will look like. Now, as a solution, I'll get two vectors. That is, for t, I'll get a vector, and for corresponding value, I'll be getting the y values. Okay, I'll be getting a vector of t and y values here. Okay, so this is based on RK4 methods. So RK2 methods we have seen. There are like RK3, RK4 methods. This is based on RK4 methods. Another important highlight is it has adaptive step size to reduce error. That is earlier, if you remember, this h was always a constant, right? We fixed h to be 0.1 or 0.01. That is always declared beginning of the program. Okay, but here what happens is MATLAB automatically takes an h value in such a way that it reduces the overall error. That is already automatically chosen by MATLAB. You don't have to think about it. So that is what is meant by the step size is adaptive based on the MATLAB chooses in such a way that it reduces the overall error. Is this clear? So now let us try to solve the previous problem using ODE 45 and then we look at one more example problem. So what happens is, this is how the ODE solver looks like. You have to use the keyword and the variables that I have is t and y. That is dy by dt. The variables are t and y. And my function is saved in this ODE, first ODE file. Let us look at that first. Okay. It takes in a variable t and y. It calculates minus 2ty and that is given as an output. Okay. Dy is the output. That is how my ODE function looks like. Now my limits are t0 to tn, where t0 is 0, tn is 5, and my initial guess is y0, where y0 is 1. So everything is given to me. Now let me just clear. I'll run the code. Okay. So here I'll get. Am I still in the meeting? So in case I have like a network issue, please to stay in the meeting itself. We'll restart it. Okay. Okay, I hope I'm still in the meeting. So what happens is you run the ODE using this T solve and Y solve, you'll be getting two vectors. Let us see that. See, you get T solve, which is like a 77. So this is a vector like this. It starts from 0, it ends at 5. And you can see here the step size is 125, 0.125. Again, it was 0.125, but here the step size is different. What's the difference between 0 point? No, 125 itself, right? So let me just see what is the step size changing. Okay, that is T solve. Solve. You have just a second. 1, 2. Let me, how many, what is the length here? 1 to 77. T solve 2 to 77. So basically what will happen is it will be T1 minus T2, then will be T2 minus T3, then finally you'll be getting T76 minus T77. I just want to see what the step size is. Yeah. So let me just look at the step size that is there in this answer. So earlier the step size was 125, 125, 125, and here you can see at some point the step size changed to 0.0914. And again it would automatically change to 0.00, 0.0664. See, Matlab is automatically changing the step size in such a way that it can reduce the error. Okay, this is what I said. It's not using a constant step size h. It keeps changing. Okay, so now when I plot it, I'm getting the similar plot. Okay, so this is how we use the ODE 45. Now we have another problem which was discussed. So that is you have a concentration along a PFR where dC by dV is equal to minus half of C 1.25. So instead of minus 2T by, this is the function that you have to solve. When V is equal to 0, your C is equal to 1. Okay, this is your initial value. So this part is your function fun. Okay, and when V is equal to 0, your Tc is equal to 1. This is your initial value. And I need to know the volume of volumes. I need to know the concentration when volume is 1, 5, 10 using ODE 45. So how do you do that? So let me share Matlab. Let me just show you how the ODE syntax works. Help ODE 45. Okay. So that is ODE 45 solves a differential equation. What happens is if you give here ODE T span Y0 for an entire T span, it will give you the Y out. Okay. But if you want to have like a particular T value, so T span is it's a two element vector from T0 to T final or a vector with several time points. That is, you can break the T span into various checkpoints T0, T1, T final. If you specify more than two time points, that is other than two T0, T final, if you're adding more time points, timestamps here, ODE will return interpolated solution at that requested times. Okay, requested times only. So if you're giving just T0 and T end, you will be getting an entire vector of T zone. Okay, but if you're giving in between, if you're giving timestamps, so for example, our previous question they had asked to get the value at t equal to 10, 20 and all. Okay, if you give that values also in between, the ODE will only give you the answer for the required timestamps. I know it's a bit confusing, so let's try to do that. So this is how the function look. So my initial, when b is equal to 0, my c is equal to 1. This is my initial condition. Now earlier I gave vn to be 5. Instead of that, let me give vn to be 1, 5, 10. Okay, and v span will become, so when I run this, clear CLC. I am running this section and my vspan is this. Earlier my vspan was just 0, 5. Now my vspan is 0, 1, 5, 10. Okay, I have like timestamps here. Now I'm using a function pfr to have my function. Okay, that is minus 0.5 z raised to 1.25 for a given value of v and c. I get dc like this. I put that here. My variables are v and c, and vspan I use for 0, 1, 5, 10, and initial value is z0. I run this here. Okay, I'm running the whole thing. So just a second. I think I just clear CLC. I'll run section by section. Okay, now you see here, VSOL has just 0, 1, 5, 10, and my CSOL has corresponding concentrations. Okay, when V is equal to 0, my C value is 1. When V is equal to 1, my C is equal to 0.6243. When V is equal to 5, so on. Okay, just for that particular volume stamps only we have the concentration. If in case of this, if I had given like this, okay, in case of this, if I had given this, now check the size of CSOL, okay? CSOL was only having four values. Now we can see CSOL has 45 values. Why? Because the Matlab itself has taken the H values. So it could be any values. It will finally distribute values from V equal to 0 to V equal to 10. Or V equal to 5 here in the case, okay? So this is what you get. Now I've done a small comparison with Hume's method. Okay, so with Hume's method, we'll just calculate from 0 to 5. So here h is equal to 0.1 and v value is equal to 5. What we do is we do a timestamp. This thing we already know. We create a vector of time. Okay, and you calculate how many n times you have to run the loop. You declare all the y values to be 0 and your first y value to be 0, c0. Then you calculate the Hume's method function k1 and k2. You put that into the equation, you get yi plus 1. Okay, now we plot also in the same plot. So now when we compare the answer, okay, I'm not sure if it is very clear. I'll just show you here. The answer that you get using Hume's method and answer that you get using the ODE 45 are exactly matching. Is this clear? Any doubts? How to use ODE 45? So apart from this, there are other solvers also, ODE 45, ODE 23, ODE 113 and all. So these are used for two different cases. One is called as stiff equations and non-stiff equations. At this point of time, this might be a little bit more information. So if you want, you can read the slide. I'll upload this. But in the next week, I'll be discussing this in detail. Okay, so you can understand what is stiff equation and non-stiff equation in the following classes. So I'm not spending time here because we are already running out of time. Okay. Now we have Rangakutta higher order method. So RK3 method means there will be K2, K1, K2, K3, and the order of accuracy is h raised to 4. Other one was h square. Okay, that is the power was 2. Here the power is 10. Sorry, here the power is 4. Okay. Now the other method is RK4 method, which means it will have K1, K2, K3, and K4, and the order of accuracy is 5. Now the most famously used one is RK4 methods, and this is how the formula looks like. It could be a bit, what you say, calculation intensive because you have to calculate all K1, K2, K3, K4, but it's a very, very accurate method because see the order of accuracy is 5 because of that. It's a very, very accurate method. So I hope you know how to calculate K1, K2, K3, K4. Once you calculate all three, you have to just put it in the equation. You'll be getting the yi plus 1. Okay, so let's try to do that. So this is a standard RK4 method. Everything remains the same. T0, Y0, T, and the H is I'm taking 0.1 and declaring my T, declaring my Y, and my initial Y value is nothing but Y0. Now this is why how I calculate K1, K2, K3. So what is my fund? My fund is this thing, minus 2Ty. Okay, my fund is this minus 2Ty. So I calculate it for Ti, Yi, Ti plus H by 2, Ti plus Sk1 by 2, whatever is given in the equation. Okay, whatever is given in this equation. Whatever is given in this equation, you have to calculate the function there. You get the K1, K2, K3. You have to just put it in the equation h by 6, K1 plus K2, 2K2 plus 2K3 plus K4. That is the equation that you have. You'll get Yi plus 1. Again, you are plotting it. Clear. CLC. I'll run. So you can see my behavior is the same itself. My error I'm getting E0, e raised to minus 0.6. Let me change this by a factor of 10. Let me see what is happening. See, from minus 0.6, it went to minus 0, minus 1, 0. That is minus 10. So this is by a factor of, what is the order of accuracy? The order of accuracy is 4. It became 10 raised to 4. So the order of accuracy is 4 here. That is why we say it is a highly accurate method compared to the previous methods that we saw. But it is like computationally a bit expensive because you have to calculate all K1, K2, K3 and K4. Now let us calculate the how each of the error is working. So this is a local truncation error and global truncation error, which we have already seen in the previous classes. Just a second, just give me a second. Sorry. So you know what is Euler's, you already know what is local truncation error and local and global truncation error. Local truncation error is when you are using one particular formula, such an iterative formula once, it is called as a local truncation error. But here you can see you are running the same formula multiple times, like in n iterations in the loop you are running it. So what happens is that your error gets accumulated. So in the first step when you use the formula, there would have been a certain error. So that error gets accumulated when you use that formula repeatedly. So then you get what is called as a global truncation error. That gets accumulated over entire computational domain as a numerical method is applied repeatedly. So likewise, whatever we are trying right now in this class, we only looked at global truncation error because we are running the formula multiple times. So as we saw here, Euler's method has an order of accuracy 1 and Hume's method has an order of accuracy 2 and RK3 has an order of accuracy 3 and RK4 has an order of accuracy 4. So this is what we saw, the global truncation error. If you want to understand it more deeply, what you can do is we can do a comparative study. So that is what we have done here. Just a second. Okay. You have the T0 value, V0 value, T and is, I'm just calculating it from 0 to 1. Okay, I can calculate to 0 to 5 also, that is completely fine. Now my h I'm taking to be different and a vector of values 0 0.1, 0 0.005, 0 0.01, and like that I'm taking a vector of values. So what I do is I for different values of h, I compute my answer using different methods and then I start to compare them. So this is my how my true value is calculated, exponential minus tn square. And I'm just declaring error to be all zeros. Before the program starts, I'm declaring error to be all zeros. Now what I do is I run a loop so that in every loop, h takes a particular value from this vector. Okay, first it takes 0 0.1. After it takes 0 0.1, I calculate how many times the loop has to run. Okay, the loop has to run for tn minus t0 divided by h. Now what I do is I write a separate function for my Euler. So my Euler function looks like this. It takes what all variable, it takes the initial t0, y0, it takes the h value and it takes how many times the loop has to run. So this my Euler takes is y0, t0, h and n. Okay, rest what happens, t end is nothing but t0 plus nh. Just rearrange the formula for n, you'll be getting t end. Now I'm declaring my t vector, I'm declaring my y vector, and the first y value is nothing but y0. And this is the same formula for Euler's method that we saw. Okay, I calculate my new y, and my final answer is the last value of y. Okay, so that is given as my output. The same thing I do for my Hunes also. It takes in T0, Y0, H and N. Okay, it calculates K1, K2 and it puts into the equation. I get the answer. So similarly, I do it for RK, my RK4. It takes Y0, T0, H and N, calculates K1, K2, K3, K4, calculates my Y value and my last value I output. So now I got a different values. For different H values, the loop keeps running and it gets added into this error thing. Okay. So let me just see clear CLC. I'll run this section by section. So this is what I get. Okay. And you can see for error 1 comma I. So what is 1? 1 is the row number, right? So my error is basically having 3 rows. This error value is a matrix. Error value has a matrix. It has 3 rows. Okay, and multiple columns. My first row is for Euler. My second row is for Hune. And my third row is for RK4. And my first column will be for, what is the H value? 0.1. Next H value will be 0.05, so on. So likewise, my entries will be added here. Okay. So after running this, let's see how my values looks like. So let me just print error. See, it looks like this. This is for Euler's. The second row is for Hunes and the third row is for RK4. This is for H is equal to 0.1, S is equal to 0.05 and so on. Now what you do for calculating error, we have already seen in the previous classes, what you have to do is you have to plot the log of H versus log of error. So for each of the methods, so for the Euler's method, I plot the log of H. H is already given as a vector here. And from the error, what I do, I only plot the first row, log of the first row. Now next to my plot will be log of H, and for Hunes it will be log of the second row and log of H, and for RK4 it will be log of the third row. And I'm keeping the line width to be 2 and I'm adding the legend Euler, Hunes and RK4. So let me run this. But before that, let me just close this. Yeah. Let me run the section. Okay. This is what I get. You can see the slopes are different. Okay. So earlier in our previous classes, we have said that if you are plotting log of H versus, sorry, small letter H. That is, if you are plotting log of H versus log of error, you will be getting a straight line. Okay. Line. And the slope of the straight line will give you the N. That is the order of accuracy. We've already seen that in the earlier classes. So you can see Euler's, Hunes, and RK4, everything gives you a straight line, but it is having different slopes. How do you calculate the value of the slope? You have to just take the x values here and the y values at the one end, and you have to just subtract, right? That is y1 minus y2 divided by x1 minus x2. Similarly for this. So if you want, you can directly do it from the graph, or else what you do is, calculate the value here. I take the log of error, log of hold, and I calculate the last value minus the first value. This is a h end minus h1, and this is the error values end minus error value 1, and then you can calculate the slopes. So this is how I get. The slope of the first line, that is Euler's method, is 1.02, which means the order is 1. And the second is 1.99, which is very close to 2. And the third is 3.98, which is very close to 4. So this is first order, this is second order, and this is fourth order. Is this clear? Any doubts? Okay. So I hope the concepts are clear. Now let's try to solve the problems. So this is our first problem that we have for today. That is explicit Euler's method we have to apply. Here the function we are looking at is dt by dt is equal to minus beta t minus 4. That is change in temperature with respect to time. Beta is a constant which is 0.5. And this is a true function. After, if you're doing analytically, if you are integrating this, this is the function that you get. Initial value is at time t equal to 0, your temperature is 30. Now what you have to do is you have to compute T2. So basically your integration limit is 0 to 2. Okay, and there are certain things that you have to use. First you have to use h is equal to 0.1 and see and tell what is the value at t equal to 2, and you have to compute the error, and you have to repeat the same thing for h is equal to 0.01 and h is equal to 0.001. And from here you can understand as you're changing h value, your error value also changes. From that you can see what is the order of accuracy for the Euler's explicit method. So this is what you have to do. So as we used to do in the previous classes, those who have access to Matlab, please open it and try to code this. Otherwise, the other ones can just use a pen and paper and let me know the answer. I'll always encourage you to do it in Matlab along with the class so that in case you have any doubts, you can just ask me then and there. So I'll give you a few minutes and then we'll discuss the answer. So let's discuss the answer. So the Euler's explicit method. Anybody need more time? So the function we are looking at is dy by dt is equal to minus beta times y minus 4. Okay, the initial value is at t equal to 0, your y value is 30, and I'm looking till the integration limit of t and equal to 2. My initial h value, I'm taking it to be 0.1. So my n will become nothing but tn minus t0 divided by h. My beta value is 0.5, which is directly given in the question. I take the t values, t vector from t0 to tn with the step size of h. My y, I'm declaring everything to be 0. Then I say that my first y value is nothing but y0. Then what I do is I solve the Euler's explicit equation, run the loop from 1 to n, and my fi is nothing but, it is calculated using this function. Okay, it takes in a value of t and y and it calculates minus 0.5 multiplied by y minus 4. Basically, that equation that is given in the question, and that output is given out of the function. Okay, and this function takes that value, and my new value is yi plus h times this fi. I get the new y value. I plot the t and y, and I also calculate what's the true value here. And what is my error? Error is different between the true value and the y value. Okay. And the final error that I need is the last value's error. So y true and minus the y what I get using the Euler's explicit method, its last value. So let me just run this. So this is the behavior that I'm getting. And the answer is temperature at t equal to 2, my temperature is 13.3206 and my error is 0.2442. Okay, so this answers my A and B part of the question. Now what I have to do is I have to decrease the
Ma'am,
exact. Yes, yes, yes. Yeah.
ma'am, here instead of giving me the Tn at 2, can I give the Tn is 5? And while executing in the command prompt, can I give T of 2? Will it give the same solution, ma'am?
T of 2, how do you give? You can't. Okay, so I'll tell you one thing. Right now here Tn is equal to 5. Okay, I'm
Yeah, ma'am.
running this. Okay, now if you have to get for t equal to 2 the values, you can't just give here. See, your y value is like this, right? This is okay. This is your t vector. Your t vector is this. It
Okay.
goes from
Instead of
0 to 0.5.
okay.
Okay,
Hmm.
and your y vector is this. So here. Okay, so if you need a t equal to 2, look what is the index of t equal to 2. That is 21st value. Okay,
Okay.
you can take the 21st value of y. That will be correct. So let us
Okay.
take y 21. So that is giving me 13.3206. Is that the answer that I got earlier? Yes, 13.3206.
Okay, ma'am.
Okay, you need to have some way to find out what index it is. Otherwise, what you do is you keep that as a last limit. So you anyway know that is the last value that you're gonna get.
Okay, ma'am.
Yeah. So t equal to 2. So now what happens is I'll just run it again for 0.1. So 0.1, my error is 0.2442. Now again, let me change the h value, decrease them by a factor of 10. My error, you can see it again decreased by a factor of 10. Okay, it was 0.2442, it became 0.024. Again, decreasing by a factor of 10, my error value is again decreased by a factor of 10. What does it mean? It means that my order of accuracy is 1. Okay, is this clear? Okay, I hope it is clear. Now let us move forward to the next question then. This is the same question, but this time we are trying for a large step size. Okay, so first step size, what you're trying to do is we need to obtain TH, where H is what? 1. So basically, you're starting with T equal to 0 to T equal to H, where H is equal to 1. And next time what you have to do is you have to compute with h equal to 2, and what I need to get is a t10. Okay, it will be 2, sorry, 2 times h means it is t4. So basically the same code itself, just that you're playing around with your integration limit and your h value. Okay, here the integration limit is, so here the h value is 1 and my integration limit is 5. Here my h value is 2 and my integration limit is 10. Am I making it right? Yeah. If the integration here the h value is 4 and my integration limit is 20. So you can see it is actually changing by a factor of 5. Okay. So whatever my h value is, my end integration limit is actually 5 times the h value. It has to be 5h. So you have to report what is the last value in all the different cases. Okay, and based on this, you have to tell what is the limiting value of h. Limiting value of h means when you keep changing high, you know that this equation is only stable when your h is very, very small. So if you're using h larger value, what happens is at a certain point, you'll understand that the code is diverging. So what will happen is we'll plot for every case, and for one of the plots, you will see that the h is going wavering. So that value of h will be the limiting value of h. So I'll give you 2-3 minutes and then we'll discuss the answer. If you have got the answer, please do put in the chat box. Okay, so that I know that some of you have done it and then we can start the discussion. Any answers? Yeah, of course. This was the problem, minus beta t minus 4. I'll give you 2-3 minutes more and then we'll discuss. We'll share the next slide. 2 more minutes and then we'll discuss because we are running out of time. So let's look at the solutions. So what we do is everything is the same, y0, t, h, everything is the same. So here what we do is h, and when h we write as 1, the tn is calculated as 5 times h. Uh, yeah, yeah, somebody has given me the answer, good. So try to do it for other ones also. By that time, I'll discuss the codes to others. So Tn, you take it as 5 times h. So when h is equal to 1, your Tn is 5, h is equal to 2, your Tn is 10, so on, okay? And then you have to calculate how many times you have to run the loop. Beta is already calculated. Your t, you calculate the vectors t0 to tn, which is step size of h. Now zeros, y you declare all to be zeros. Then you say the first y value is y0. You run the loop from 1 to n times. This is your fi value, and this is your Euler's explicit formula. You plot the t and y, and then you will have the actual value, and you calculate what is the error between them. Okay, and the last error is what you require. So no, it's okay. You can also calculate the maximum error. So let me just run the code for h is equal to 1. What will happen? The value is 4.8125. Yes, because you've got the correct answer, and the error is 3.06. And if you look at the plot, you can see it is exponentially decreasing. That's what we saw in the first problem, right? So the behavior is okay. Now let me increase the value of h. Now I'm taking h is equal to 2. So now t end will be 5. See, t end will be 2 times 5, that is 10. Okay. I'm running it again. Now we can see the behavior. It is a sharp decrease, and then it is going to, it is like a saturated curve. And the error, you can see it is increasing 9.56 something. Yeah. H is equal to 2, it is 4. Yes, you've got the right. H is equal to 2, the value is 4. Yes, you've got the right answer. Now let us do for h is equal to, what was given in the question? Let me just check once again. It is 1, 2, 4, 6. Okay. So let's do that. 1, 2, now 4, we'll run it, and you will be getting answer minus 22. Let's look at the curve. You can see the curve is going all wavering. Okay. Yeah, I've got the right answer, Vikash. Now, for h is equal to 6, when you run it, you're getting minus 182. Again, the graph, you can see it is gone all wavering. So what happens is, this is the values that has been shown to you. And yeah, you've got the right answer, because and you can see till h equal to this here, when h was equal to 2, you got an okayish curve. Okay, so it was like a sharp decline and then a straight line. But afterwards, you have got a very wayward part. So what happens is, here you can say h is equal to 2 is the limiting value of h. Okay, is this clear? Any more doubts in this question? If not, let's move on to the next question. So this is a rate of change of liquid height in a tank with respect to time. dH by dt is given as, yeah, good. So dH by dt is given as Qi minus Q0 divided by A. H is the height, T is the time, Qi is the inflow rate, and Qo is the outflow rate, and A is a cross-sectional area. A value of A is a constant, Qi is a constant, A is a constant. A is where, because A is a constant, G is 9.8, and Q0 is calculated as A square root of 2GH. A is known to you, G is known to you, H is the only unknown. And you have to calculate when T equal, this is the initial condition. When T equal to 0, H is equal to 0.1. You have to use ODE 45 to compute the liquid height at 10, 20, 40, 60. So remember, the T span has to be 0, 10, 20, 40, 60. We will have to do it for the entire T span. Only the required T spans are required. There should be a function that will write the Qi minus Q0 divided by A. And you know what's the starting, you know what is the limit. It has to be a T-span, you already know, and the initial value is 0.1. I hope I've given you all the info. Try to do this and we'll discuss answer in like 2-3 minutes. Okay, once you've got the answer, please put it in the chat box. I've got some answers, so let's discuss. So, as you know, the ODE 45, am I audible? Open
Yes, madam.
C0 is equal to 0. We have the initial value. It equal to and I'm keeping it at 10, 20. For that, my entire T span will become 0, 10, 20, 40, 60. Now I have to check what is the prop 3 fund. So this is how I've coded the prop 3 fund. It has all the variables A, Qi, G, whatever constants was given in the question. Then I calculate Q0 as A square root of 2GH. My DH by dt is Qi minus Q0 divided by A. That is the output that I give out of this question, out of this function. And then this is my problem. This is my T span and this is my initial guess. So let us run this step by step. Okay. So when I run this, what happens is this is a solution that I get for t equal to 0. For t equal to 0, my height is 0.1. When t equal to 10, my height is 0.2831. There might be, yeah, some of you got the wrong answer. Maybe just check the signs properly, okay, of the equation. It is, the equation is Qi minus Q0. Qi is a constant, Q0 is A square root of 2GH. Okay, just check you've got the signs right. And for t equal to 20, the answer is, so I'll just print the t, so t span also. I think that is better. T solve. Yeah, sorry. So this is how you get for 0, 0.1. For height, time 10, height is 0.2831. For 20, the height is 0.3744. For height 40, answer is 0.4547. The answer is 0.4825. So these are the answers. Do you have any questions? And if you want to plot it, I've given the plot here. Just a second. This is how the plot looks like. This is time versus height. You can just plot the t sol and y sol. It looks like this. For 0, it is 0.1 and it keeps increasing according to time, which you can see here. And it goes up to 0.4825. Yes. This is RK6 method. This is not discussed in the class. So only RK4 is discussed. So here the only thing is you have like 6Ks, K1, K2, K3, K4, K5, and K6. And this is how it has been combined. H by 90, and this is the value. So it might be a little bit time consuming, but still try to do this. And what you have to do is, this is a function minus 2ty. And initial condition is when t equal to 0, y is equal to 1. This is the exact analytical solution. Try to plot y versus t for this RK Ragakuta sixth order method. We don't usually use this method because even though Ragakuta is similar to RK4. Okay. So what we do is, I'll give you some time. Try to do this and then we'll discuss the answer. I've got some answer. So let us discuss. So this algo is like pretty straightforward. Just you should like learn to code the functions properly. Okay, so we already have a function myfund which we kept using in. Just that when you give a t and y, it calculates a corresponding 2ty, the function for you. So t0 is equal to 0, y0 is equal to 1, that is the initial value. T and I'm calculating till 5. So the span is from 0 to 5. T and I'm using 0.1. This is the number of times I have to run the loop, and my t value I'm just giving it as a column vector from 0 to 5, and y initially I'm declaring all to be 0, and then I'm telling the first y value is the 1. Y value is equal to y0, which is equal to 1. Then I calculate k1. Make sure you don't make a mistake here. Okay, the t and y's has to be given correctly according to the formula. So this is k1, k2, k3, k4, k5, and k6. And you have to put everything together. H by 90, 7 k1, 32 k2, 12 k3, 32 k4, 7 k4, and 12 k6. Okay, that you get the yi plus 1. You have to just plot it. So I'll just show you how the plot looks like. Okay, this is how the plot looks, and the error is 0.0315. Let's see what happens when you are using h by L over h value. Okay, okay, it's not doing much of a difference. Make sure just see that I've coded it correctly. I might have made a mistake, but I think it's right. So just see, this is how we code it, and the function, it remains almost the same. Lot of people doesn't use this RK6 method because it's a lot of computation and you can get a pretty good accuracy in RK4 itself. And I'm not very sure about the error, that term that I get here. Okay, so just go through the code. I can just you can just take a screenshot of this code if needed and see if it is the formulas that has been actually given to you in the PPT. Yeah, because why do you need time? Are you still doing it? Okay, okay, okay. Are you getting different value for error? Vikash? I'm not sure how to pronounce your name. Is it Vikas or Vikash? Okay. Error is not required. I've not asked you about that in the question. I'm just thinking like usually we should be getting the different factor, right? I'm not getting that for RK6. I'm not sure if that is a property of RK6 or is it a mistake from my side. Just calculate the error once. Okay, for 0.1, just take 0.1 and calculate the error once. So error, this is the true value and the error will be nothing but your y true minus y, and just calculate the maximum error. And let me know if you're getting the same value as 0.0315. I can wait. Have we calculated the error? So because of time, I'm just moving on to the next question. Do you have an answer? Okay, it's already past 8, so I'll just move on to the next question. If you have any doubts, please let me know in the next class, okay? So this is a question. We have like a population change with respect to time. This is a function Rp minus P by K, where P is the population, R is the growth rate, and K is the carrying capacity. So initial, when T equal to the first year, so when T equal to 1, your population is 10. So we have to calculate at the end of 100 years. In the first year, the population is 10. Uh, and at t equal to 100, what is the population? R value is given to you, the constant R and constant K value is given to you. Okay, you can use ODE 45 directly. Let me know the answer. After that, we'll discuss. Once you get the answer, please put it in the chat box. Let me check. I've got an answer. So yeah, let us check. So the T-span what we have want is from t equal to 1 to first year to 100th year, and the initial population is 10. So the ODE fund, this is a function that is giving the ODE equation. T-span is from 1 to 100 and the initial P0 is 10. So let us look at this function also. ODE function, it looks like this. R is equal to 0.065 and K is equal to 38, and this is a function RP multiplied by 1 minus P by K. Okay, and let me run this. Let me just close the figure. This is what I get. This is how the function is increasing when year is equal to first year my population is 10, and the last year when 100 my population is 37.83. If you want to get that from the answer, what you can do is you have to just type pop the nth value, that is 37.83. Let me look at the solutions. Yeah, most of you have got it right. Yeah, because you've got it right. So that is the answer. Any queries? So that is the end of today's session. We don't have any more questions. Any further doubts? If you don't, okay. Yeah, if you don't have any further doubts, as we have already gone beyond 8 p.m., I'll be ending the session now. Thank you so much. Let's meet next Friday, the same time, 6 to 8 p.m., and we'll discuss the next week's class. Yeah, thank you. Thank you all. I'll be ending the session now. Thank you so much for the people who responded also. I want everybody to attempt the questions and give me the answers. Even if the answers are wrong, it's fine. Let's try to learn this together. Okay? Okay, thank you all. I'm ending the session.